Okay, so today we're going to talk about the Antarctic Circumpolar current, which is the big current that goes around Antarctica. This will be a relatively short video. There's some nice schematics of how it works in the Colling book in chapter 5, section 5. There's some discussion in Valis as well, but that's a bit abstract. Okay, so you might remember this figure that we talked about in the MOC discussion, where all of the different overturning circulations kind of link up to the ACC. So the ACC is like the hub of these spokes in the global ocean wheel. That's an important piece. You can see that there's both deep waters coming in toward the ACC, whether it's the North Atlantic, the Pacific, or the Indian Ocean deep water. There's an Antarctic intermediate water, or mode water, MW mode water, South Antarctic mode water, or there's the Antarctic intermediate water. These are coming like out in the top, and then there's of course the Antarctic bottom water at the bottom, which is the most common water type on Earth because it fills most of the bottom 2 kilometers or so of the ocean in all 3 basins. Okay. So here is a side view, including fluxes at the surface from this paper by John Marshall and Kevin Spear, which is a nice review article on the ACC and how it works. And notice that they're talking about the meridional overturning circulation through Southern Ocean upwelling. So it's really focused on the overturning circulation, looking from the side. So now when we look from the side, we can see this the Antarctic bottom water coming in, spreading upward. We can see the deep waters coming in at mid depths and heading towards the pole. And then we see the mode water and the intermediate water up here and the surface coming back the other direction. This is the global MOC. So in the Atlantic, we would see much more intense deep water pathways. Take a look now at the cooling and heating, and then the wind stresses. So you see westerly winds in the around 40 north and south, and then you see the trade winds in between about 25 north and south. So this means that the Ekman transport of the upper ocean is away from the ACC, away from Antarctica, across the top of the ACC. So the question becomes, what waters go up and fill into that, and then why is there this circulation that has this pattern like this? That's the story we want to talk today. And whether it relates to the ACC itself, which is also coming out of the page, going in the same direction as the winds. Here it is looking from above. Now we see the ACC going around and around in the same direction as the winds, coming from the west to the east. And we talked about this from the perspective of geostrophic balance, with there being low pressure all around Antarctica and then relatively higher pressure up here in the as we get into the regions where there are gyres. The subtropics. That's one way of thinking about it, but we'll try and figure out how that works, because we're thinking about it from the perspective of maybe the Spherical transport or other pieces of that story. So if you think of it as an eastern boundary and upwelling boundary current, that sort of makes sense, except it's so huge that it doesn't quite make sense. It's the span of that Ekman upwelling is much, much larger than it is in the eastern boundary current, so it might be only 1 deformation radius wide. Here it is many, many degrees of latitude, all the way from about Drake's Passage across to the Antarctic Peninsula here, which is the narrowest point, but significantly longer when you go from Africa to Antarctica in this direction. Okay. Here's temperature, salinity, and oxygen down below. And the temperature you might expect is stratified with warm stuff on the top, cold stuff on the bottom. The Antarctic bottom water is quite cold, and the mode waters and even the upper deep waters are pretty warm. This salt signature shows you this, that there is this big anomaly in the deep waters coming up in terms of what their salinity is. Much fresher water up above. And interestingly, there's an inversion in salinity, so that Antarctic bottom water is actually fresher than the deep water above it. Is that true? Sorry, the numbers are very small for me. Okay, just zoomed in to double check that. Yes, that's true. It's about 0.1 PSU fresher on these Antarctic layers, than Antarctic bottom water layers, than the deep water layers that are coming in. And then oxygen, remember, oxygen is refreshed when you're last at the surface and then is slowly consumed after it goes subsurface. You can't see much of a signature of higher oxygen in the Antarctic bottom water. There's a little bit of one way down at the bottom in this layer that's labeled 240 over the waters above it. So it is at least higher oxygen at the bottom, and then decreasingly lower oxygen as we go up into the yellow tongue in the middle. And then the purple layers of that intermediate water and mode water on the top are really fresh, very young water. So so we start to get a sense of why we have this upward intermediate older water. That's the deep water that's coming up, the bottom water that's relatively younger, and the intermediate and mode waters are relatively younger as well. And so we've talked about this a lot in relative to the pressure, where we talked about there being low pressure on this side and then higher pressure across. So we know that the ACC will have a large geostrophic component because of this pressure signature at the surface. We don't know immediately how, although we have discussed the fact that it's unlike the gyres, the ACC has pretty substantial pressure deviations even at 1,500 meters depth. So it goes quite deep, in fact, all the way to the bottom in some places. There are small gyres, the Weddell gyre and the Ross gyre, and the Weddell C and the Ross C. And then there are normal sort of subtropical gyres up here against where the Agulhas is coming out, and then also in the Brazil current region and the East Australian region. Those are relatively standard gyres. Some of you have looked at those for your gyre paper, but this range in between, it doesn't make a whole lot of sense to have a gyre there, because we can't really do geostrophy in sphere drift, because what does it lean on is the way I'm putting it. But let's just think about it from the perspective of the pressure. If our geostrophic transport is the pressure gradient in the x direction, that is in the zonal direction, gives us our meridional geostrophic transport. What if we take a whole band all the way around Antarctica, enclosing on both sides? Then we can do that integral, and here I'm doing it in spherical coordinates, which instead of the x gradient, I've got this is what you would get if you did a longitude integral, which is the equivalent of the x gradient. So I would get the integral of r times the longitude going from 0 to 2 pi for this side. So f times vg. So this is the integrated transport that I'd be looking for. And then look on the other side, I would get 1 or rho naught, and then I would do a longitudinal integral of pressure, which just says to give me the pressure difference between 0 and 2 pi. But there is no pressure difference between 0 and 2 pi, because 0 and 2 pi are the same place. So that would be 0, which means that there is no meridional transport, geostrophic meridional transport allowed in the ACC if there's nothing for it to lean on, if you can enclose this whole surface. So that's interesting, because we just saw lots and lots of meridional transports. Meridional transport, meridional transport, meridional transport. So how is that possible? What's going on with this transport of properties, but maybe not mean fluid, that's setting up these deep water, intermediate water, and bottom water exchanges? What about the sphere-drift relation? We can play the same game with the sphere-drift relation. We do an integral. Now we want to do the same integral that we do with the dA to dx, and we do it in the longitude. And again, we come up with that there would be no sphere-drift relation, at least based on the surface pressure, the way that we have been approximating it. That would also be 0. So what's going on? Well, actually, One way to think about the ACC is that it's really not full depth, but there is an important sill, and then there is flow below, there could be flow below the sill. If that's the case, then you could have, now there's no periodicity, at least at the depths below the sill, and so you could do a geostrophic transport below the sill depth. And if we set up an idealized version of the ACC like this, with a gyre to the north, a gyre to the south, so maybe the Ross or Weddell gyres, and then a reentrant channel in the middle. And then we put, let's see what this is the buoyancy forcing, so it's warm on one side, cold on the other. Here is the Ekman transport, which is basically saying that we have winds blowing along where the current is. And then here is the Ekman upwelling, which says that since we have constant, there's zero upwelling here, but there's upwelling on this side, downwelling on this side, which gives us a subtropical gyre and a polar gyre, subpolar gyre on either side of the front. This is a simplified ACC setup from Jeff Vallis, based on the Henning and Vallis papers. And then if we look from the side, what we get is a transport something like this. So here's the depth of the sill. Here is the surface Ekman transport. We can't have geostrophic transport in between, as we just said, but we can have geostrophic transport below. So you actually get a closed cell, which is Ekman at the top, geostrophic transport below the sill, upward. And then if you think about, if you have cooling and warming, you need to have upward transport and downward transport like this to make the whole circuit work out. So what does that do to the isopycnals? So here is the ACC in that region. And if you have this kind of a circulation, you're basically lifting up cold water all along here, pushing down warm water all along there. So you expect that the isopycnals are going to get totally vertical under that kind of a steady transport. That also does not look like the real ACC. The ACC has, these intervening layers and these kind of sloping isopycnals all the way across. In order to get this is actually two numerical model simulations. The one on the left is using a numerical model that does not have eddies in it, and the one on the right is a numerical model that does have eddies in it. So the one that does not have eddies has a simplified just horizontal diffusion operator, whereas the eddies transport fluid however they want to transport fluid. As we talked a lot about in sort of the thermocline thinking, not so much in the context of eddies, when you have flow that's relatively low energy density, it needs to flow along the isopycnal surfaces, because overturning isopycnal surfaces requires a lot of energy density. So these eddies, though they are powerful, and maybe this is one of the world's most powerful eddy fields, those eddies do not have that level of energy density. Neither does the ACC to overturn the isopycnals and to make mixing happen here frequently, at least. But what they do have is they have the ability to extract potential energy from where these interfaces would be, tilts them over this way. Now, how can they do that? Big eddies are geostrophic. We just said there's no net geostrophic transport across. That's because, and there is no net geostrophic transport across up here in the region above the sill, which is shown here with the dotted lines. But what there is there's intermittent geostrophic transport. So geostrophic eddies going one direction, geostrophic eddies going the other direction. Every time they go north, they are carrying relatively one density class, and every time they go south, they're carrying a different density class. That's actually going to end up being a net transport of temperature, salinity, oxygen, etc., by eddies across this open region above the sill. So you can think of something like this, where you might have a snapshot of the eddying flow. So here we're looking in the longitude depth plane, and you would have in and out and in and out flowing. And because in order to get this in and out and in and out in the geostrophic transport, you would actually have hot and cold anomalies like this, the way that it's shown with the C's and H's, in such a way that, sorry, this is a terrible aspect ratio, C's and H's like this, in such a way that there is a net transport into the page here of hot stuff, out of the page here of cold stuff. And so across the ACC, you would actually be transporting heat, because hot stuff would be going north, cold stuff would be going south. That's what the eddies are doing. Why would they be moving hot stuff north or south? Actually, And that is because they're trying to extract that potential energy from the flow. Now, if you averaged in a thickness weighted flow, okay, this is a little bit complicated. If we don't average in horizontal slices, but we average weighting the thick part of each of these layers more than the thin part, then we would find that the net transport in this upper layer, B1 layer, would be into the page because it would be dominated by this thick, hot region. In the second layer, we would have slightly thicker cold regions. So we would have expected to be a little bit cold. We would expect to have the out of the page transport. And then the bottom layer, we would expect to also to have the out of the page transport in the thickness weighted. So in this thickness weighting, this gives us a different sense of what's going on than we would get if we just average in the horizontal, which would actually give us no transport north or south. That's what we did when we did the pure zonal mean, not a thickness weighted zonal mean. So the thickness weighting allows us to see different layers might actually be transporting north or south, even though in zonal mean at a particular depth, there's no net transport north or south. The reason why that's important is because each of these layers has hot or cold water in it. So this net transport actually is a transport of hot water north in one direction and cold water in the other directions. If that makes sense. We talked very briefly about something similar happening in the atmosphere, where warm tropical air and cold polar air would be exchanged whenever we had troughs or basically storms in the jet stream. If this warm tropical air actually exchanges or is dissipated, and the cold polar air is the exchanges mixed up or dissipated, then you are actually, there's a net heat transport implied by that. And so even beyond the even beyond the Hadley cell, you're still transporting heat poleward in the atmosphere through this kind of an eddying process. So this is the same kind of game, except we're transporting heat through an eddying process in the ocean. What do these eddies look like? In the atmosphere, they're huge. That might just be a few wavelengths for the whole Earth, but in the ocean, because the deformation radius is much smaller, you can see, this is looking at sea surface temperature, you can see a lot of these eddies sort of crinkling the flow as you look around in different parts of the basin, different parts of the Southern Ocean. So they're quite small eddies, but they are individually all doing this process of transporting warm stuff one direction, cold stuff the other direction, and systematically. Relatedly, you might think about the stress from layer to layer to layer to layer, from top to the bottom. The wind stress would be balanced by a stress transfer from one layer to the next layer to the next layer to the next layer. We haven't talked about this kind of layer by layer momentum budgets very much. I don't want to go into too much detail. You can go check out Ballast if you're interested about how this works out. But basically, the way the ACC works is you put wind stress on the top, bottom stress on the bottom has to balance it. So it accelerates until that balance is found. But how much shear you get across the layer is actually intimately related to that north-south transport of eddies through this term, which is called the form drag term, where each deviation in the interface is actually allowing the opportunity to provide stress from one of those density layers down to the next, down to the next, down to the next, and transfer that stress downward in the thickness weighted sense. So each of those layers is thickness weighted in this kind of conception, and that sets up how each of the layers is accelerated. That sets up the shear from layer to layer to layer. And so the eddy efficiency essentially in how quickly that shear is carried from top to bottom is what sets up which has to do with the overturning circulation, is how this balance works out. So we talked about the horizontal transport around and around the ACC, and we talked about the overturning circulation And now we're recognizing that because the overturning circulation has to do with the meridional transport of heat by the eddies, in the process of extracting potential energy, those two are actually now intimately related, because the way you get to the surface velocity field is through figuring out how much meridional overturning is required in order to close those budgets. So it's linked back and forth and back and forth. So we can think of something like this, where we might have a mean transport like this, going around and around. This is just a slice through an idealized ACC with a wind stress on it and heat flux kind of schematic. This is from a different paper, but this is from an Abernathy paper, but this is actually from the review article describing the Abernathy paper. But here's the Ekman transport, the below the sill Antarctic bottom water transport down here, this upward and downward. This stream function is what drives the flow going around that way. The eddies, on average, if in thickness weighted coordinates, are actually opposing the direction of the Ekman transport. So they are moving warm stuff southward, cold stuff northward, in such a way that if you add these two together, the circulation induced by the eddies, the circulation induced by the Ekman transport, this is what you get for the so-called residual transport, which is the residual of the eddy part extracting that potential energy that's being put in by this overturning, which is tending to steepen the isopycnals. It's overturning the opposite direction, extracting that energy by putting warm stuff on top of cold stuff. And the net, add these two together, is where we can see the Antarctic bottom water being injected at the bottom, the upwelling deep water coming up to the surface, the diverging transport at the surface, and then the intermediate waters and mode waters heading northward up into the gyre region at the top. If you release a tracer into this flow, the tracer does not follow the mean overturning. It does not follow the eddy-induced overturning. It follows their sum, this residual overturning. And so a tracer released at the surface slides down along the isopycnals of the, this is probably showing that it's coming up along the deep water here. But you also could have tracked any one of these water masses, the Antarctic bottom water, the intermediate water, et cetera, by putting a tracer in. And you notice that this tracer, as it's spreading out, is not, it was released within one isopycnal, and it has spread out within that isopycnal as the eddies and the mean circulation stir it up, but it doesn't cross into neighboring isopycnals. And so if you put all this together, you get some similarity between the two hemispheres, where you have deep water formation, and it should be dissimilar, I guess. But so anyway, North Atlantic deep water going this way, coming up into the ACC, coming back as the Antarctic intermediate water, or back as the Antarctic bottom water, depending on whether it's been cooled or transferred at the surface by the Ekman transport. And then superimposed on that, we have the gyres. So the deep water and the bottom water are slowly exchanging, mixing, and then returning in this kind of a flow pattern. So, in conclusion, the ACC is one of the largest currents in the world. Winds drive it through surface stresses that need to be balanced by bottom stresses. Eddies are an important part of that downward stress transfer in this residual mean or thickness weighted mean sense. And relatedly, the Ekman and eddy-driven overturning are in opposition, and they affect the formation of Antarctic intermediate water and Antarctic bottom water. So you have to add those two pieces together to get the picture of those overturnings in the ACC, and it's very similar to the atmospheric Ferrel cell in the way that it works, that all these pieces work out. The end.